All right, let's get started. Welcome to discussion. Hopefully, you all have made significant progress on P1. So, how many people have submitted P1 already? Okay, good, fair number. For the rest of you, are you still getting problems with tests? Or are you blocked on something else? Anybody who's here who's having a problem with tests? Okay, so yeah, test should be good by now. So you should, once you have finished your program, you should be able to run tests and check whether what grade you get. Okay. So today we're going to talk about the next project, even before we have finished submitting the first project. So project 2 is about processes and scheduling, as you can see on screen. Hopefully everyone can see on screen. So we have slightly different due dates for this project because there are like two significant parts of it. One of the first part will be due on the 3rd of October. The second will be due on the 10th of October, a week from when P2 is due. Okay, so when compared to P1, both of these parts are going to be significantly more difficult. So I highly recommend that once you've submitted P1, you get started on these right away. Okay. So today we're going to look at the first part of it, which is the shell program. So the details are like all on this page, and to give you like a short summary of what you'll be doing, you'll be writing your own shell program. So what you see when you go to a terminal is basically your shell running. Like when you type ls, it's showing you what's in the directory. So you're going to emulate this behavior by writing your own program. Okay, and to do this, we're actually going to need to look at how you can create a process, how you can redirect input and output, how you can get the process to run whatever it is that you want to run, and so on and so forth. Okay, so make sure you take a look at the all the details of the project. So there will be some specifications, like how you can how you should declare your int main, and like what commands you're supposed to support in your shell program. Okay. So, all right. So, oh yeah, there's one more significant difference from P1 to P2. In P1, we released all of the tests for your project, which means that if you pass all the tests in P1, you'll be getting a perfect grade. In P2, we will not be doing that. In P2, we'll be releasing only some of the tests, like around 80% of the tests, and some tests will only be run when you hand in your program. What this means is that you have to be really careful about like all the corner cases that you'll find in the specification of the program. So if you find something confusing, make sure that you send email and you talk to us and you find out like whether you have to handle this case or you have to handle that other case. Don't make assumptions thinking that because it's not explicitly said in the document you don't have to handle something. It's better to get it clarified, because the remaining 20% of the test which will not release is going to look at things like, have you handled all these corner cases correctly? So if you get the basic functionality working, and if you pass all the tests that we make public, you'll get around 80% of your grade. But if you want a perfect grade, if you want the final 20%, you have to really read the document carefully, make sure you look at all the corner cases and code all that in. Okay? Make sense? All right. So let's see. So let's get to like some of the things I'm demoing. Yeah? Uh-huh. Right. Well, it was right. It clearly said what format your input and output should be. You had an example output in the code. Obviously, right? I mean, like I can't keep telling you like if you don't find A in this document, you have to assume A. So yeah, I mean, so we will try our best, of course, to give you all the information that you need, and you're entirely welcome to sort of like email us and ask us whatever it is that you find confusing or doubtful. Okay. All right. So let's get to it. So we're going to write a program. I already have it, huh? Okay. So we're going to write a new program. Right, anyway, which will create a new process. So we have talked in class about like how processes are created and how they are managed and like how do you context switch and all, but you haven't actually looked at the API for how you create a process and how you make it do whatever it is that you want, tell it to do, right? So that's what we're going to do in today's class. So let's set up our usual stuff. So I'm just like writing a dummy program to show you how things are going to work. So the first thing we're going to do in this sort of program is we're going to do a fork. Okay. So fork is the system call that allows you to create a new process, and it's a very strange system call. As in, it's not obvious what the result of running the system call is going to be, right? So what fork will do is it will duplicate your current process and create and put it inside another process. So whatever, like we're running test.c, right? So the test binary will be duplicated and it will be put in the second process, and it will start running at this point after fork returns. Okay. So at this point there's only one process. Then there's fork, which means that you now have two processes which are running the same thing, and then the rest of the code will be executed by both the processes. Okay. Yeah. Oh, okay. To find. That's not what I wanted. Is this better? Okay. All right. As I was saying, in line 5 we have only one process. On line 6 we call fork, which will create a new process. Both of these processes will be running the exact same program. So 8 is going to be actually executed by two different processes, and so is return 0. Okay. Now if I've explained this correctly, you should be able to make sense of like what will happen now. Okay. So are people able to understand why after is being printed twice? Okay. So one after is from the parent process and one is from the child process. So we're going to make this really clear. All right. Okay. So what we are going to do is we're going to print the process ID and see what result we get. Okay. I am hoping this is the correct way, although it may not be. Okay. So the number that you're seeing there is the ID of the process that's executing that code. So you can see that's like two different IDs. One is from the parent process and one is from the child process. So let me make that a little bit more clearer by printing the ID of the parent also. So you have before, which is printed out by the parent, which is at like 439. You have after, which is also printed out by the parent, and then you have after, which is printed out by the child, which is at 440. Clear so far? Okay. So fork is sort of like one of the main ways in which you create a process in Linux. But as you can see, it's a very weird way to create a process. Like it's not very helpful if like your child process does the exact same thing as your parent process. So first, we will see how we can differentiate between what the child and the parent process can do. So one way to look at that is to see what fork returns to you, right? So if you look at the man page, which is insanely long, on return value, it says on success the PID of the child process is returned in the parent and a 0 is returned in the child. So this is crucial because the return value of fork will be different in both of the processes that we are currently running. In fact, it will be the only difference at that when the two processes are created. Okay, so what we can do is depending upon the value of the fork, we can see whether we are in the child or we are in the parent process. So let me see. So we have the return code in RC. So if it's 0, it means that we are in the child. If it's not 0 but a positive value, it means we are in the parent. If it's less than 0, it means that fork failed. Okay, and one of the ways in which you can see how what happened is to use p error. How many people have used p error before here? No one. Okay. Right. Okay. So what p error will do is, before that, when you call a system call in Linux, if it fails, what it will do is it will set a global variable called error number, ERRNO. Okay. And what p error will do is it will go look at that error number and then it will print that along with any string that you're going to give it. Okay. So here we say fork failed. Okay, so if fork really fails, the spearer will make sure that it prints the string that we gave it along with the reason for like why fork failed. So that will be helpful for debugging. Okay, so let's see. So here we're gonna say child here, and here we're gonna say parent. Okay, are things making sense so far? So like feel free to interrupt me like at any point of time. So let's see what happens now. Okay, so here we see that based on the return value of 4, we are able to see which is the parent and which is the child, right? So if you look at the parent ID, the parent ID is like 476 and the child ID is 477, as we sort of expect, right? So what this gives us the ability to do is to do different things in your child process based on this different things in your child process based on this return code. So you can have the parent do something and you can have the child do something different, as we are doing here, because we're printing child and parent differently based on the return code. So this is the sort of basic mechanism to sort of like create a child and then have it do something different from the parent. Are things clear so far? Okay. Now, in order to do your shell program, you actually need to be able to tell the child to do something based on input that's given to the shell. For example, when we say ls, the ls is a binary command, by the way, which is now running and you're seeing the output of ls, right? So in order to sort of like duplicate this behavior, you'll have to tell the child to run ls for you. Okay, and so the command which ls tells us where the ls binary is located. Okay, so it's located in this point. So what we want to do is we want to tell the child to take this binary and then run it for us. Okay, so the way we do that is using a command called execvp. Okay, so exec generally is a system call which allows you to take a process and then run something differently inside the same process. Okay, it's also kind of a weird system call in that execvp will only return if it fails. If it succeeds, what will happen is your current process will sort of like die and will be replaced by whatever it is that you're giving execvp. For example, let's say we want the child to do ls for us, right? So the child will die and will be replaced by ls, which will then run for us. So it is a weird system call, and I'll demonstrate it and you can see how clear it is. So here we're going to use execvp. So execvp actually requires us to use a new file. So we're including that file. We might as well actually get the arguments for that from here. Okay. So this is the sort of like signature of execvp, and what it's actually telling us is that the first command, the constant cat star file, is going to be the new program that we want execvp to run. For example, this could be bin/ls, right, in the example that we're going to look at. And we have another argument, which is argv. And this is an array which is terminated by null. And so these are going to be the arguments we are passing to the new program. When we see an example, hopefully this will become clearer to you. So what we're going to do is we're going to run ls using execvp inside the child. So first, we're going to set up our own sort of argument list. Okay. So here I'm just declaring an array of like 4 character pointers. One sort of like interesting side thing to notice: what's the size of a char in Linux or x86? Does anyone know? It's 1 byte. Good. What's the size of a pointer to a char? Right. So this actually is just storing an address like we saw in class before. So 0x000123 whatever. And so the address needs, it's based on the architecture of the system. So for a 32-bit system, the address is 32 bits or 4 bytes. Okay. So what's sort of interesting is that we only actually require space for like for if you're pointing to a character which is like a single byte, you actually need 4 bytes to point to that single byte. So that's based on the architecture that we have. All right, so moving on. So let's set up some arguments for it. So we're going to run ls. The first thing that we are going to set up, the 0th argument, is going to be where the binary is. Okay. And I am using a system call to sort of put this inside this argument. So what str_doop does is it will malloc some memory. Hopefully by this point of time everybody knows what malloc is, right? Is there anyone who doesn't? Okay, good. So it'll allocate some memory for you using malloc, and it'll copy whatever string that you're giving here into that newly allocated memory. And then this pointer, myarg v of 0, is going to point to that newly allocated memory. Does it make sense? Okay. So what we're saying is that we'd like to run ls for this thing, and we could run it without any arguments. Okay. And the way we do that is we'd say the very next argument for this is null. Null indicating that there are no more arguments and that we are done with our command. So just execute bin/ls without any arguments. Okay. If you look at the argument list for execvp, you see that we're not passing in the number of arguments. We are just passing in an array of like argv. And the way the system calculates how many arguments there are is we're looking where null is. Okay, I could put any number of arguments after null, and the system is just going to disregard that. It's only going to look at where the first null value is. Okay, so let's go ahead and actually run execvp. So we're going to say my rg is 0 and sorry, and then my rg. Okay, and remember that I said that execvp will only return if it failed, so we can put something like this here, execvp failed. Okay, and this will only be printed if we have either done something wrong, which is highly possible, or for some reason in the system it wasn't able to use execvp to replace our child process with ls. Okay, So let's see if this compiles. I might need more, yeah, I need more headers. So let's look at where this is. So this is in string.h. By the way, this is the way that you sort of like go about adding headers. We just look at the man page, find out where anything is located, and then like put it in. Okay, so that compiles. And let's look at what's going on. Okay, so what you're seeing here is the ls output from the child. Okay, so the child is getting created, so it is saying like its id is 574, and then it's going ahead and it's doing ls for us. Okay, so now an interesting thing to note here is that when we run this, we see that's like the terminal sort of like stops after it's produced that output, right? And the reason for that is we have now created two different processes. There's the child process and there's the parent process, and we haven't said anything about like when they should end or when the control should come back to the terminal. So there's an easy way to actually do this in the program. So you could say that your parent program, which is right here, can wait for the child program. Okay, what this means is it will wait until the child has been created, is going to run, and after it's finished running, this command will return. You can actually pass arguments to wait. Depending, if you have many children, you can pass arguments saying I want to wait for this child but not for this child. You can pass an ID into wait and you can see what happens. Okay, but in this case we have only one child, so we're just going to go ahead and say I'm just going to wait for default for my one child. So let's see what happens now. Okay. So what you're seeing here is this is before our system calls. Like we're initially starting out with like one process 585. The child is created at 586. It does the ls thing. It completes, and then we have the parent which waited for the child to complete. Now printing out saying that the child is done. Yes. But so so when you run a program in the background, you see similar behavior. Basically, we're instantiating new processes and we are waiting for them to complete. Here we are ensuring that your parent is waiting for the child, and then once the parent completes, everything has finished, and then the command control passes back. Okay, so I showed that because like that's sort of one of the crucial differences between waiting for your child to complete and then just like letting processes run. Okay, yeah. Right. No, that's a good question. So when you call execvp, it's the same process, the same structure, the same ID and everything, but what it's execute is going to be replaced using execvp. So it wipes out all its commands, its instructions, and then fills it with whatever we give in execvp. Okay, but it's going to be the same process. The ID is going to be the same thing. Okay? Does it make sense? Yeah. Right.
The command from the shell was in the 9th stage, right?
Like before we called wait, like if we didn't call wait?
Yes.
So yes, so it had just executed both of these things and it was waiting for them to complete. The shell program, I mean, which is what you're going to write in your assignment, basically works by taking whatever command that we give, spawning a new process, and then running that command inside that process, and then waiting for it to complete. Okay, and in that particular case, we did that. We created a new process, which was running test, which in turn created a new process. So now your shell is waiting for all the children to complete, which is why you saw that gap. In this case, everything is sort of more ordered. You create the parent creates the child, it waits for the child to complete, so now there's no hanging processes, and then it comes back to the parent exits, and then it comes back to the shell. So everything is more orderly now. Okay? Does everything make sense so far? Yeah? So, I mean, we are not using execvp to sort of do that. We are going to use wait to do that. And wait doesn't depend on execvp. So wait has its sort of it's an OS system call. So the OS always knows when a process starts and when a process completes. So it's going to use OS resources to sort of do that. Okay. Any more questions? Yeah. So everything is wiped out. So when you do execvp, the new program has no information about the old program. So those are arguments that we are passing in explicitly to execvp, right? Oh, if you're asking about what happens to the memory, that those are like, we are not freeing that memory. You're right in that that's memory that's allocated and will be wasted sort of. If this is a long running program, this would be a problem. Okay. But in this particular case, we are just like passing those things explicitly to execvp. So it's on the stack for execvp. If you remember how we did function calls, we would copy all the arguments into a stack and then we would execute that function. So the stack for execvp now contains everything in argv. So we don't really care about what happens to that memory after we call that function. All right. We had another question, I think. Yeah. Yes. So the thing is that when you're typing in ls and your shell is actually doing a bunch of stuff to figure out where that executable is. So there's this thing called the shell path, which is all the locations where you look for executables when you type something in. So the shell that you're writing, and we're sort of writing in this like demo, doesn't really know how to do all of that. So you can actually get your environments and then check in those environments if that file is there. That's up to you. But if you give the full path, you will always find the command. Okay. If we didn't do all that environment things, it will check whether this is present in the same directory. Okay. If it's present in the same directory, of course we'll be able to find it. Otherwise, you'll have an error. Okay. So now yes. Right, that's what I'm exactly going to do now. Okay, so we'll just see. So let's pass minus L to ls and see what happens. So let's just do that right now and see. So what we're doing is that like the minus L will give you details on ls. So we're seeing things like what is the size of the file. Like it has 90 bytes, test has 8686 bytes, and test.c has 663 bytes. And these are all the permissions on like different files in the system. Note that test is a binary, so you have the executable permission on the binary. Okay, and these are like who's the owner of the file and so on and so forth. Okay, so the same output is what we're going to get inside our program. So we're going to say my argv 1 is strdup minus L. Then we're going to replace this with 3. Okay, so and there we have it. The same program is now giving us it's accepting flags for ls, and then we're able to see the output that we saw before. Okay, yeah. So let me see. Are you asking about like here or this? Yes. Yes. That sort of convention here. So even if you try to write a C program, right? If you look at like argc and argv, you will find that the program name itself is always the first argument. So that's the convention that we are following here. Okay. With me so far? Okay. So we're going to look at something else, and this will be useful when you're doing redirection in shells. So what do I mean by redirections? So right now, when you do ls minus L, all of the output is going to your screen, right? So if we did this, what happens is that all of the output that was getting printed to the screen is now being redirected to our file. So if we used cat, we will find the same output that we had in ls. Interestingly though, if you look at this, it says that the size of out is 0, right? So at the moment while we were typing this command, out was created but had no contents. Whereas if you look at it now, of course out has contents based on the ls. So it's been created but it doesn't have any contents, but once the command is complete, now it has all the contents. Okay, so this is the sort of like the um, good example of redirection. There's also pipes. So have people here used pipes in Unix? Okay, all right. So to sort of demo that, we see that ls minus l gives us like so many lines of output. If we wanted to see how many lines there are, a different way to do this is send this to another program called word count, and in word count you just like check how many lines there are, and it says there are 5 lines. Okay, now the sort of cool thing about pipes is that we are not creating any temporary files for this, right? So we're not saying we're going to pipe without, we're going to put the output of ls minus l into some file, then we're going to read that file and then do word count on that, right? Instead, we are saying that whatever ls minus l is outputting, push all of that to the word count program and then run word count program on that output as if it was a file. Okay, so sort of a side note is that this is called the sort of like Unix philosophy, wherein you don't have like really big and bulky programs. You have really small programs which are fast and do whatever it is that they do efficiently, and you use something like this, like pipes, to string together all of these programs and to get whatever effect that you want. Okay. Any questions so far? Okay. So let's see how you can do something like this in our program. So one of the sort of conventional things about Unix is that there are 3 file descriptors associated with each process. Do people know what file descriptors are? Okay. So when you open a file, you get a handle to that file saying this is the file that I've opened, which we call a file descriptor. Okay. So it's just a way for the program and for the OS to know what are the files that you have opened. It's, for example, if you opened a.text, you'll get a file handle for that, and the rest of the program you can just use that file handle instead of saying a.text everywhere. So just shorthand for that. Okay. So to come back to our main point, every process in Unix has 3 file descriptors sort of associated with it: 0, 1, and 2, which are shorthand for 0 is standard input, 1 is standard output, and 2 is standard error. Okay. So what do I mean by this? Whenever we do whenever we run a program and we are doing scanf, for example, we are actually getting input from the user via standard input. Okay. So, and whenever we are printing something out, we are actually printing something to standard output. So all of the printfs that we are seeing here are actually going to standard output. Okay. So let me sort of demonstrate that. So here we have the child which has been created, and it has a get PID. Now what we're going to do is we're going to close the file descriptor associated with standard output. Okay, since this is the file descriptor into which all of our output is going, what will happen is after it says child and the process ID, we won't be able to see any output because we have closed the file descriptor and we no longer can print anything. Okay. I know it's a sort of slightly confusing concept, but we will see what I mean in a second. Okay, so now when you run the test program, you see what's going on. It says ls tried to write to the file descriptor, but since we closed it before we did all those printfs, it couldn't actually do it, and it complains saying it's a bad file descriptor. Okay. What we are going to do is, we closed one, but we're now going to open a new file and then pass some flags. Okay. And the interesting thing about Unix is, I'm opening a new file. So this file needs a file descriptor, correct? And Unix will always assign the lowest available file descriptor. Since we closed one is now open for is available for taking, and so new file will be allocated the file descriptor of 1. Now printf is expecting that we should be writing everything to 1. So what will happen is that the output, we will no longer get an error, but we will start writing everything like from ls minus l into this new file. Okay, so let's check that out. All right, shift out.